Okay, so this video is going to be about a major topic in this class, which is Fourier series. This video is just going to introduce Fourier series, the definition, and some formulas involved. And then in the next video, we will look at a lot of examples. All right, so before we get into that, though, let's just talk about a main theme, so to speak, of just ECE 45 as a whole. This is something that we're going to come back to again and again in this class, and that's that we want to understand the I/O, the input-output properties of LTI systems, which we've learned about, a little bit about anyway. In particular, we want to understand these I/O properties by first understanding how these systems behave for sinusoidal, or even more generally, as we've seen in the eigenfunction video, for sinusoidal or complex exponential inputs. Okay, so essentially we want to look at how these systems react when we put in sinusoids or even complex exponentials, and then try and somehow generalize that to take so that we can understand more complicated functions as well. Okay, and this is going to be leading us into Fourier series and Fourier transform. And I'll just make another note. By linearity, the L of LTI, if we have a sum of these inputs going into our system, or actually, I shouldn't even say sum, I should even say a linear combination. We have a linear combination of these inputs going into our system. Then we know is, I'll say, the same linear combination of the corresponding outputs. And I'll show you exactly what I mean in a second. Okay, corresponding meaning the outputs for all of these inputs that we made into a linear combination. Okay, so this is kind of just rehashing the definition of linearity, but that's not a bad thing. But let me show you some examples. Okay, so it's pretty simple, actually. It's exactly what you'd hope to happen. So let's say I have 3 cosine of 4t plus pi over 3, just some random inputs. But now we're going to add to it 7 sine of 3t minus pi over 4. And let's say I send that into a system with some frequency response. So we're going to start talking about frequency response more generally for LTI systems. So far, we've really only talked about it specifically for RLC circuits, but just for now, you can think of this, pretend it's a circuit, but I'll just leave it like that. Okay, then we know what should come out, right? Because RLC circuits are linear. LTI systems, the L means they're linear. And so we know what comes out from this first input. Okay, we know what the output is of the second input. And so when we add them, the output we get from this entire signal should just be a sum of the corresponding outputs. So if you remember from a previous video, what do we get for the output of that signal? We get 3. And then this frequency response tells us how much to multiply that amplitude by. We multiply it by the magnitude of the frequency response at the frequency we're sending that signal in with. Okay. And then we have our cosine of the same frequency plus pi over 3, plus now the phase, the angle of our frequency response, again, at the frequency 4 that sinusoid is oscillating with. Okay, so that is the output from that first input. And by linearity, I can just add that to the output from the second input, which would be 7 magnitude of the frequency response at this frequency 3 times sine of 3t minus pi over 4 plus the angle of the frequency response when omega is 3. Okay, so you can see how we can start building up more complicated functions just from these sinusoids. Okay, and also from the eigenfunction video, we can generalize this a little bit to complex exponentials. So let's say I send this signal in to my system. Oops, that's better. Then what do I get out? Well, we know what we get out from this complex exponential itself, right? Remember the eigenfunction video. E to the j omega t goes into a system with frequency response h of omega. What comes out? That word eigenfunction should remind you, it's the exact same as our input, just multiplied by the frequency response. So this one relationship is kind of, as we said in that video, encapsulating the two relationships we derived for just cosine and sine. And it turns out that we can kind of use this mathematical statement to capture both of those input-output relations at once using complex numbers. Okay, so this is the case, so I'm going to use that now. So I have e to the 8jt, so omega is 8 here. So I know what I should get out from just this is h of what? Well, h at that frequency, the frequency response at that frequency 8 times e to the 8jt. But then again, by linearity, I'm just multiplying by this constant. Okay, so I can keep that constant there. And then minus that constant 11 times the times the frequency response. So now we have this negative 13 as our frequency. So our frequency response at negative 13, that is the frequency of that complex exponential signal, and then times that same signal right there. Okay, I just used this property twice and then used linearity to say, oh, I have a linear combination of these two signals, 5 times the first minus 11 times the second. Well, that means my output should be the same linear combination, 5 and negative 11, of the corresponding outputs. Okay. So that's what I meant over here, the same linear combination of the corresponding outputs. That's what I mean. All right. So this process, we can generalize this to any finite number of sinusoids, or complex exponentials in some linear combination. Okay, so as long as I have finitely many, we can just use this process over and over. But a big question is, what about infinite sums? Okay, and that is where Fourier series are going to come into the picture. What about infinite sums? Okay, of those sinusoids are complex exponentials. And it turns out we can analyze virtually any function we would care about in practice. Okay, so it turns out that we can analyze virtually any function that we would ever care about in anything we would ever do. It turns out there are kind of these kind of strange cases that we're not going to deal with in this class, where things are not always so simple. But with infinite sums, we can analyze, it turns out, virtually any periodic function. And then to actually analyze any function we care about in practice, we're going to need integrals, and that's where the Fourier transform comes into the picture. Okay, so for now, we're just going to deal with infinite sums and look at Fourier series, but in the future, for now, with Fourier series, in the future, with Fourier transforms. Okay. All right. So let's get into the definition of Fourier series. So Fourier series. All right. So definition. So this is just for periodic functions, Fourier series. So if f is periodic, that's a really big attribute of Fourier series with period t. Okay, and omega naught is going to be 2 pi over t. Okay. Actually, you know, I'm going to add just one line here. I was just thinking, what about infinite sums? This, I'll just say, gives us Fourier series. So I just thought this would be clear. This gives us Fourier series. And I'll just write here, it turns out we can analyze virtually any function. So that's kind of a separate point now. So infinite sums, I just want to be really clear, are going to be with Fourier series. And then in general, any function we care about in practice, either we can use Fourier series or in the future, we'll use Fourier transforms once we get there. Okay, great. So now let's go on to Fourier series. So f is periodic. It's got period t. It's got some fundamental frequency. Then the Fourier series, okay, for f, so f is going to have a Fourier series, is, and what is it? I'll write it down here, then we can talk about it. So it's going to be the sum, infinite sum of f sub n. Okay, these are going to be what we call the Fourier series coefficients. They're complex numbers, times e to the j n omega naught t. Okay, so here are complex exponentials. And I'll just write it all down and then we'll go back and talk about it a little bit. The constants f sub n are called the Fourier series coefficients. Okay. And in general, they can be complex numbers. So these are complex numbers. Okay, so let's just take a moment and try and look at what this equation is saying. Okay, there's a lot going on here. So this is saying that we have our periodic function f of t, and it's really an amazing thing that this line is saying. It's saying that that periodic function f of t, okay, it could be doing anything, right? Maybe it's this periodic function or something like that. Any periodic function, okay, at least for our purposes, can be written as a sum, possibly an infinite sum, of these complex exponentials. These are very nice, well-behaved functions. All they're doing is going around and around and around in the complex plane. That's all they're doing. It's just a number in polar form. And as this angle here increases, as t increases, they're just going around and around and around in the complex plane. So you might say, well, how could you possibly represent f of t using these functions? Well, that's where these Fourier series coefficients come into play. Okay, so these Fourier series coefficients, the things I multiply these complex exponential functions by, these Fourier series coefficients f sub n, those are what give me control and would allow me to actually create this function f of t we wanted out of these much simpler functions. Okay, and specifically, these functions here aren't just any old complex exponentials. They have very specific frequencies. They're all integer multiples, right? In a sum, the summation variable is always an integer. They're integer multiples of the fundamental frequency. Okay, so we don't have just any old complex exponentials here with any frequency. Their frequencies are specifically integer multiples of the fundamental frequency of my f of t. Okay, so this is a really amazing thing. I mean, you would not think that this had to be the case from the get-go, right? You give me a periodic function and I write it in terms of these simpler functions multiplied by constants. It's really amazing. And there's some really cool animations online of this process that maybe we can look at in the future. Okay, you could also look them up yourself. All right. So it's pretty cool. And you can imagine why this would be useful, because now I have f of t written as a linear combination, a big infinite sum of these constants times these simple functions, and those functions are really easy to analyze with LTI systems, right? These are eigenfunctions. I put them in, I know exactly what comes out. What comes out is this function times the frequency response at that frequency. So this is what's going to allow us to understand the input-output relationship for LTI systems for general periodic functions, because we can write them in terms of these simpler functions and then get the output for those simpler functions and use linearity to add all those outputs up using these coefficients. Okay, so that's kind of the big picture where we're going with this. We're not going to see that in this video, but I just thought I'd mention that up front. Okay, so the big question you probably have is, how can we determine the Fourier series coefficients, the f sub n's, when we're given the function f of t, right? That's the big question. Because if you're given f of t and I know the period and fundamental frequency, then all of these functions are set, right? I just have a sum, I go over all the integers n, and I multiply by the fundamental frequency, and I get all these functions. The big outstanding question is, how do I ever figure out what those constants, the f sub n's, the Fourier series coefficients are? Okay, that's the big unknown in this expression. Okay, so that's what we're going to prove now, and it's a little complicated, proving this formula. Okay, it's going to take us a little bit of time, but any step along the way is kind of interesting. Okay, and at the end, we'll get actually an equation for these Fourier series coefficients f sub n when we're given this f of t. Okay, in practice, there are often a lot of other ways for us to get those f sub n's without this formula, but this formula is also very useful for some questions. So that's what we'll look at right now. So we're going to start by looking at some properties of sine and cosine that we'll need. Okay, so first property. Okay, so I'm going to look at a specific function, and I'll explain what this means in 1 second. Okay, so I'm doing 1 over the period, 1 over this period of f, this t. Now, what does this symbol mean? An integral with a t and the subscript. Okay, I didn't forget some superscript. This means here we can integrate over any interval that has length the period. So I'll just write this as interval, some constant a to t plus a. Okay. So that's what this means. So this integral, I can integrate over any period. So if the period was like 4, just to give you an example, then I could integrate from -1 to 3, right? Because that is length 4. This is like -1, and then -1 plus 4 is 3. I could integrate from -pi to 4 minus pi. I can integrate from 10 to 14, right? That's just what this means. You can integrate over any period. You get to decide. And part of problems is going to be trying to sometimes pick very nice bounds for your integral. Okay, and why does that make sense? Well, if I have some periodic function, which is where we're kind of going for this, and I want to integrate it, it doesn't really matter where I start and end that integral as long as it's got length of period, because then I'm going to always get the same answer, right? You're always going to be adding up 1 period's worth of your function, whether I move those bounds over here or where they just were. I don't know where they were, but just as an example, you're still always going to get all of the area. Obviously, you subtract this area over 1 period, no matter where you move your bars, right? Because the function's periodic. So as long as I'm integrating over a period, I'm going to get, the function on 1 period, maybe just shifted and kind of cyclically wrapped around. But I hope this is clear. I'll just do a specific example with sine. How about that? So I have sine here. Let's take a specific example so we can really see it. And let's see what happens when I integrate over 1 period. Okay, so I find that area and subtract that area, right? But what happens if I integrate over a period where I start, instead of having this period here to here, what happens if I look at the period from there to there? you can see I'm getting the exact same integral because this is the same as what I had here. And then this is actually the same in both of these places, right? But even if I start my period maybe halfway through this part of the cosine, still, I'm going to be integrating this part and this part, which is, for instance, the same as there, and then subtracting that area right there. Okay, so the integral over this period is the exact same as over this one. Okay, and you can kind of imagine this is true for any periodic function in general. So that's kind of why this comes up with periodic functions. As long as you integrate over a period, you're integrating essentially the whole function, at least that one period's worth. Doesn't matter where that period starts and ends. Okay, anyway, so that's kind of the rationale for why we sometimes integrate over a period like that. And so let's see what this integral actually is. Okay, so let's just pick some values. So a t plus a of cosine n omega naught t dt. Right, so we got to integrate over a period. I'll just let a be some number and then integrate over a period starting at a. And now let's do this integral. What do we get? We get 1 over t, and when I integrate cosine, I just get sine, but then I have to use the chain rule, okay, and make sure that all of the constants work out. Okay, so that's the integral, because when I differentiate this, I get cosine of n omega naught t, that's good. But then by the chain rule, I'd get multiplied by n omega naught, and so I just have to cancel that. Okay, hopefully this is clear. And we're integrating from a to t plus a. Okay, so what am I going to get? I'm going to get 1 over n omega naught t. Okay, and then I'm going to take this function and plug in the top limit. So I get sine of n omega naught t plus a minus sine of n omega naught a. Okay. So now what? Oh, and by the way, I should have mentioned here I divided by n. Okay, n is going to be an integer. Okay, n is going to be one of our integers. This sum is just saying let n start at negative infinity, go to infinity, and go over, essentially just go over all of the integers. Okay, but you never actually plug in negative infinity or infinity. It's just saying go over all the integers. And so right here, one of the integers could be 0, so I can't divide by 0. So I'll just make a note here. This line only works if n is not equal to 0. And later on, we'll come back and consider the 0 case. Okay, so I have n omega naught t. Now, what do I have inside here? Well, I have this big T, which I know is 2 pi over omega naught. Why would that be useful to plug in? Because then it would cancel that omega naught. So I get sine of n omega naught t, but omega naught times t is just 2 pi. I just bring that to the other side. Omega naught times t is just 2 pi. So I get 2 pi n plus n times omega naught a minus sine of n times omega naught a. Well, what have we done here? Well, we've simplified our function to the point where, here, I'll just make a note about that t, by the way. We've simplified our function to the point where now I have sine of n omega naught a, and I have sine of n omega naught a plus 2 pi n. Well, n is always an integer, so this is just shifting by some integer multiple of 2 pi away from this value. But we know that sine is 2 pi periodic, right? If I take my sine function and I look at any point, what happens when I go 2 pi and into to the right of that point? Well, I get the exact same value, right? It's 2 pi periodic. Same with if I went 4 pi, I would get the exact same value. Sine is periodic with period 2 pi. So what does that mean for us? That means that if I have this value sine of n omega naught a, and I look at the value sine of n omega naught a plus any integer multiple of 2 pi, I'm going to get the same value. Okay, so these are actually equal. This actually equals sine of n omega naught a. So when I subtract them, of course, I get 0. Okay, so essentially what I'm saying is that if we integrate cosine over a period, this specific cosine n omega naught t, we're just going to get 0. Okay, which you probably could have understood from maybe drawing a picture, but this is a more rigorous way to do it. All right, so what about going back? What if n actually equals 0? Let's consider that case. Okay, so we'd have cosine of 0 times omega naught times t. This is when n equals 0. Okay, but that's just cosine of 0, which is 1. what happens when I integrate the constant 1 over a period? Well, I'm just going to get the length of that period, which is t. So we're going to get 1 over t times t, which is just 1. Okay, so in summary, 1 over t integral over a period of cosine n omega naught t, it equals one of two things. I forgot the dt here. Okay, it either equals 0 or 1. It equals 1 if n is 0, and it equals 0 otherwise. So it turns out to be a pretty simple function. And by the way, what is this construction doing? Well, it's integrating over a period, then dividing by the length of that period. It's kind of just looking, it's saying what's the average value of this function over a period. That's all it's saying. So if this n is not equal to 0, I have some cosine function oscillating at some frequency. What's the average value over a period? Well, you can kind of see, you know, for every value above the axis, there's a equal and opposite one, so to speak, below. And so they all cancel out to give you just 0 on average, versus if n actually equals 0, then I'm just saying what's the average value of the constant 1 function from 0 to t, and of course that average value is just 1. Okay. So that's what we get. So how about the second property? Okay, the second property, so I should say this is for any integer n. Second property also for all integer n. What happens when instead of looking at cosine, I look at sine? Turns out that always equals 0. And you can verify this on your own. It's pretty much the exact same thing. Right, when n is not 0, it's going to be 0 for the same reason as the cosine. And then when n equals 0, now sine of 0 here is actually 0, not 1. Here cosine of 0 is 1. So that's why this just always equals 0. Okay, so now let us put 1 and 2 together. And what is our favorite way to put sines and cosines together? Well, we like to make these complex exponentials out of them. So e to the j n omega naught t dt. Okay, what is that equal to? This is equal to cosine of n omega naught t plus j sine n omega naught t dt. All right, that's just by Euler's formula. Now I'm going to split this integral up. I'm going to have 1 over t integral over a period of n omega naught t dt plus j times 1 over t integral over a period of sine n omega naught t dt. And now we can use properties 1 and 2 to say, oh, hey, this right here, I can use property 1 to understand what that is, and this just equals 0 by property 2. And so all I'm left with is exactly the expression I had in property 1 over t times the integral over a period of cosine n omega naught t, which we already said equals 1 if n is 0 and 0 otherwise. Okay, so that happens to be true for this complex exponential function as well. All right, so we've made a lot of progress, but there's still some to go, but not too much more. So let's get back to our question. Okay, so how do we get the Fourier series coefficients? Just to remind you, I'll write the Fourier series for f one more time, because we're going to be using this. Okay, and we're going to use a trick. So here's what the trick is. I don't know how you would come up with this on your own, but someone else came up with it, so we can use it. Okay, so we're going to multiply both sides by e to the negative j k omega naught t. Okay, and then integrate over period 2. Actually, it turns out that this type of thing we're doing now actually shows up in other areas of math too. So it's not just for this one situation. It's not like just one random trick. Actually, it's used in other places too. But okay, so this is what we're going to do. We're going to multiply both sides of this equation by this complex exponential signal and then integrate over a period. Okay, so we're going to integrate over a period. And actually, we're also going to multiply by 1 over t. You wouldn't have to do that. You can add that constant at the end, but we're also going to do that. Okay, so 1 over t times the integral over a period of f of t times e to the negative j k omega naught t dt. So we multiplied the left side by that, and then we're going to integrate over a period and multiply by 1 over t. Okay, and now we'll do the same thing for the other side. If these two are equal, then I can just do the same thing to both sides and I still get something that's equal. So I'll just throw that entire thing in. So n equals negative infinity to infinity, f sub n e to the j n omega naught t. That was my f of t. Now we're multiplying it by e to the negative j k omega naught t dt. Okay, now what can I do? Well, now I'm going to flip the integral and the sum. And turns out you can't always do that, but in this case, it turns out you can. We don't have to get into the gritty details of that, but let's just do it. So we have the integral n is negative infinity to infinity. I'll bring out the f sub n. Okay, and now what's left? I have 1 over t integral over a period of e to the j, and now I'm going to combine these exponents. Okay, so what do I get? Well, I have an n minus k, and then the j omega naught t is common to both of those. Okay, so this is what I get. And now this looks an awful lot like what we had in property 3, right? Let's see if we can get them both on the same page. So I have 1 over t times the integral over a period of e to the j times some integer times omega naught t. Okay, so what did that property 3 tell us? Okay, so this is by property 3 above. This equals what? Well, it's either going to equal 1 or 0. That's for sure. We just have to figure out the condition. Here, the condition was if that integer equals 0, and the other condition was everything else. So if this integer here, which is n minus k, equals 0, and 0 else, yeah. But of course, n minus k equaling 0, that really means that n equals k. And otherwise, that entire expression here just equals 0. So what does that tell us? Well, it tells us that in this sum, as I'm going over n, okay, k is fixed. K is something I chose at the beginning. So the sum is going over all these n's. And if n does not equal k, if we're in this case, then this term here is going to be 0. And so it's just going to be multiplying this f sub n by 0, and it's going to get rid of it. Okay, the only term in this entire infinite sum that is not zeroed out by this expression is when n equals k. Let me write that down. So the only non-zero term in the sum is when n equals k, because all the other ones, this term is 0, right? And it just zeroes it out. So the only time we get something non-zero is when n equals k. So what would the sum look like? It would look like a whole bunch of zeros. And then finally, when I get to n equals k, I'm going to have f sub k. Okay, this f sub n term. Actually, I'll even write it as f sub n because we know n equals k. I can write either one times 1, right? Finally, this expression equals 1. And then I'm going to have a whole bunch of zeros after that. Okay, and so since n equals k, I can just write that as f sub k. So this is pretty amazing. We've somehow started with just our f of t signal. We've applied this operation to it and multiplied it by this complex exponential, and somehow we end up with one of the Fourier series coefficients we wanted. So f sub k equals, and actually, you know what? I'm going to change, or I'll leave it as k so we don't get confused. I was going to change it back to n. Usually we use n. I'll just leave it like this for now. So that means this f sub k equals this expression up here. And that is how we find, this is the formula to calculate the Fourier series coefficient f sub k of a periodic function f of t. So you give me f of t, I say, okay, I want to find all these Fourier series coefficients. Here I'm using n, but down here, just because of how we went about the problem, we had it in terms of k. Typically, we write this expression with n instead of k, but I didn't want you to get confused because we've kind of been using k the whole time because we had to use n right here. But anyway, so you give me f of t, and I say, okay, I'll tell you the kth Fourier series coefficient, and you can just do this operation. Okay, so we'll see in the next video some examples of using this, but also a lot of the time we're going to be able to find the Fourier series coefficients in an easier way without having to do this integration. So we'll see examples of both of those cases in the next video, but for now, that's all I had for this one, and I'll see you in the next one.